Hey guys, this is Daniela, and I know there's some confusion about lab number 10, spectroscopy, so I wanted to give you guys a quick little breakdown that might make it a little bit easier and might make more sense. So for this lab, it actually follows lab number, I think it was 6 when we did column chromatography. So if you can think back, we did column, we ran the samples through, and then we ended up saving them for NMR. Now, we had spring break, and then we had coronavirus, and so then we never really did this lab. We got put off at the end. So in your lab experiment, when you need to talk about how you got these compounds, you are just going to go ahead and talk about what you did in lab number 6. So you might need to look back and remember and refresh yourself on what you did. Now, I want to work a very quick example just so you guys can see what I mean when I say annotate. So in lab and lecture, I'm sure you talked about NMR. We kind of talked that we were going to do it, so I'm going to give you a quick little example. Okay, so I have this compound here. Now, I don't know if this is a proton NMR, carbon NMR, or IR, because that's what you're going to have to work with. You're going to have a proton NMR, a carbon NMR, and IR. Same for this one, same for this one. And you have to label it the exact same way. Now, looking at the scale, which is in ppm, if it's on a small scale, like 0 to 5, 0 to 8, 0 to 10, I know it has to be proton NMR. That's the scale for proton NMR. If it was a larger scale, like 0 to 500, 0 to 300, that's going to be carbon NMR. And then IR is when your spectra looks inverted, and that tells you the functional groups, remember? So proton NMR is based off of the protons, carbon is the carbon splitting with depth, where they are inverse, and then IR is functional groups. So those are important things you need to remember. Okay, so the first thing I recommend you guys do is to go ahead and just label all of your protons. Just do it. So I know this has 3 protons here, right? It's a CH3. I know this one has 2 protons, right? There's the C. Carbon has to have 4 bonds, right? So carbon has 1, 2. It has to have probably 2 more bonds to make it happy. And then I have this OH group here. Okay, and then I just go ahead and label them letters. It doesn't matter as long as I understand which one is a signal that will give me a signal. So I know this carbon here. These 3 protons are in the exact same environment. Because this carbon is connected to only one thing, they're experiencing the same amount of splitting. So that means it will probably give me a signal by itself. So I'm just going to say this is A. It doesn't matter what I label it as. Dr. Groupie uses shapes. She does like a diamond sometimes or a triangle. But I don't want to do that. Shapes make it easier to tell for me when I'm grading, and then also for you guys, so you have to trace it back. Okay, so A is the first one. I don't know which one of these that is, but I know it's A. This is right here. Okay, and you can sometimes use numbers if you want. I don't really care, but just do it the same way. So I have this carbon here, right? So it's connected to a CH3 carbon and a CH2 carbon. That's different than this one because it was just connected to a CH2 carbon. So that means this will have its own signal. So I'm going to label this as B. It doesn't matter though. Okay, I'm going to keep going down the line. This CH2 is connected to a CH2 and an alcohol. So remember, these are both CH2s, but they're connected to different things. So that will give its own splitting. So I'm going to say this is C and then this is D because I have a little proton on here. Okay, so I should have in theory 4 signals. Now this is like a little theory problem. Very, very easy, very simple. So if I look at my spectra, I see 1, 2, 3, 4. That's a great sign. Now I know you guys kind of talked about this, but you should know the n+1 rule. Also, there's another way of figuring it out based off the splitting patterns. I like those a lot better. However, we won't talk about those for this video. Like I mentioned in my email, I love to do examples of these. So if you really need help, if you want me to do another Zoom meeting with examples, I completely can. I don't mind. I love it. Okay, so n+1 rule. So let's just start with A. I don't know where it's going to be, but I know I'm just going to start with it. So these 3 are going to give off a signal. and I have to figure out what is attached to it, what's going to cause it to split. So right now, it's attached to a carbon, a CH2 carbon. So how many protons is the neighbor? 2, right? Because I have 2 protons. It's not attached to anything else, right? So I'm going to put a 2 here, and then plus 1 equals 3. So that means for this signal, I'm going to see a triplet. So I hope you guys have talked about that. I'm pretty sure you guys have. So if I look up here, this is a triplet, this is a multiplet, this is a triplet, and this is a singlet. So either this one is for the CH3 or this one's for the CH3. And if you remember, downfield is over here and upfield is over here. Now when it comes to downfield and upfield, I like to think of it as downfield is the more fun side of the spectra. It's like downtown Nashville, right? It's where all the fun molecules want to go hang out and have a good time. So things like oxygen, more electronegative nitrogen, they're going to cause deshielding and shielding and pull your signals more toward this way, okay? Up here is the boring stuff. It's upfield. It's kind of like, it's your lame basic carbon, like CH3, CH2. And I think in lecture you should have received something that looked like this. It has like spectra where they kind of show up at your normal chemical shifts. I also have another one that I like. There's lots of them on the internet. I can send you guys some if you need some, but they should be basically the same. So I can either look at my chemical shifts to see where a CH3 can kind of end up, and keep in mind that the more fun molecules are on this side. Okay, so if I do that, that means the CH3, it should be somewhere, it should be this one over here, because if it's pretty far away from the alcohol. If you count, it's 1, 2, 3 carbons away. That's kind of far. So if it was closer to the alcohol, it'd be pulled more towards over here. So I know this peak here is that CH3 group. So I'm just going to put A. So that's what that A is. So I'm going to keep going down the line. So I have CH2. Let's see, what is this one connected to? So if I look at this neighbor, hold on, I'm going to erase this. Okay, so for this one here, I'm going to look at this neighbor here. So it has 3 connected to it. So that's 3 for the neighbor. Is it connected to anything else? Yes, right? So that means I have to also account for this one. I count for both of which they're connected to. So I have 3 protons here, 2 protons here, and then I add 1 for the fun of it, right? N plus 1. So that's 3, 4, 5, 6. So I'm expecting a sexlet peak. Or you can call it a multiplet. They're the same thing. So if I look, this is 3. I already have this labeled. 1, 2, 3, 4, 5, 6, and then 1, 2, 3, and 1. So obviously this one has to be my CH2 group here. So I'm going to say this is B right there. So that's corresponds. So that lets me know when I'm grading it, you think this is A, this is B, and then we're going to do C and D next, okay? So let's see. This CH2 group here, it's connected to here. So this has how many protons? 2 plus, and then this one gets a little tricky. Alcohols are kind of special. I'll talk about those in a second. But I don't think this proton is going to make a difference because of that oxygen hanging on there. So we're going to do 2 plus 1, and that's 3, so it's a triplet. So that means it has to be this one. That's the only triplet left, and it's a little bit more downfield, so it's closer to that oxygen. It makes more sense. So this one is C. Okay, and of course that leaves D for my alcohol, right? So alcohols are kind of special. If you look at your chemical shift, they can appear anywhere from 4 to 8, which is large, and then even then, sometimes alcohols don't even show up. So on your NMRs for your homework, you probably won't see an alcohol shift. This is like a perfect example, a computer-generated example. Ours is like a real example, so we really ran it, and that's what we really got. So usually alcohols don't show up. Alcohols are characteristic of having a single peak and a little bit more downfield. So if you don't see that singlet, if you don't see that broad singlet like this, or maybe like this, that means your alcohol is not there. That's okay. Just don't label it or just put alcohol not there. I'll know if it's supposed to be there, if it's not supposed to be there. I just don't want you guys to get tripped up and get confused. So this was a very, very simple example. If we were to do carbon NMR, we'd do the same thing, only I would label all of my carbons. So that's what I like to do. First, start off, go ahead and label what you have and just give it a peek assignment. And then you're going to go through and try and do your best to label everything. So this is a carbon here, so I'll say this is A, this is a carbon here, this is B, this is C, okay? And so that's how I'd go out, and I expect to see about 3 peaks, and I would use my chemical shift on the carbon table to figure that out. Or this one. It depends on which one you have. They're all basically the same. And you're going to use electronegativity more for the carbons than you will for the protons. Just think about what's getting pulled, what's getting shielded, things like that. So that is what I expect for your annotated NMRs and IRs. Oh, I'll go over a little IR example. So your IR stuff looks like this, usually. So IR tells you functional groups. So for this one, I have probably one main functional group, that alcohol group. And if you look at your IR cheat sheet, because there's also a cheat sheet for IR, it's this on the back. So it usually looks like this. If I look at alcohol or a carbon hanging off of alcohol, usually it's in the 3000, 2800, it varies. So use this as your cheat sheet also. You can Google it or you can find another one. So this peak here is for the OH. So I would say A, and then I would put here, and hold on, I'd put an A here. And so it's really important that you circle or box your functional group to tell me what functional group that is. Because if you just put A for the whole thing, I'm not going to know what you're talking about, and you might not get full credit, right? So if you just say like A, are you talking about this functional group or the fact that the carbon is connected to there? Like, what are you talking about? So go ahead and box that in for me. So when you have to annotate your NMRs and IRs, that's what we're expecting. So that's for that part. And I recommend when you're doing the assignment, before you do your lab report, annotate it first. It's going to make it 10 times easier, and I think you guys will like that better. Now, when you're writing your lab report, start off with your abstract, okay, like normal. Include information on how you got the sample. That was from lab number, I think, 6, column chromatography. You're not going to have numerical data. You're not going to have, like, 30% yield. None of that is what we're doing for this lab. So you're just going to talk about, instead, like, the role of NMR and IR in this case. So what does NMR, like, why are we using NMR, IR? What does that tell you? But just keep it general to your abstracts. I think you guys have been doing a pretty good job on that. So don't worry too much about it. And then your introduction, you need to cite your sources like normal. Include briefly that column was done. You know how we do, like, okay, column chromatography. But your main citation should be about NMR and IR. And when I say, and your compounds, acetaminophen, aspirin, caffeine. And when I say NMR, IR citations, I mean, don't give me, like, basic NMR information, like, proton NMR is this, and then cite that. Your citation should be your applications, like, why is NMR used, who uses IR, stuff like that. Like, that should be your main introduction. We're going to skip the discussion, and then we're going to do the experimental. Now, she has an example online, and this should follow with it exactly. So it's a little bit different or experimental. So you're going to have a structure of your compound. You're going to have the compound name, parentheses 1, so you're referring to it. And you're going to have a very short little paragraph on how you got that compound. So aspirin, you got it by doing 1-to-1. Caffeine, you got it by doing 1-to-2 solvent. You ran it through. Put your conditions for that. And then you're going to have a row for NMR, a row for carbon NMR, and for IR. And so what you're going to do, because you should already have it annotated, those spectras we have uploaded, you should have them already labeled out with the A, B, C, D like we did. Same thing like what I did over here. So you need to list out your signals, and you should mention what solvent they were ran in. And I'll go ahead and tell you that's chloroform D, and that's what we denote as CDCl3 or CDCl6. It depends. She has her example in there. I'll tell you which one it is. But chloroform D is your solvent, and then if you're doing carbon NMR, you need to note what NMR you use it on, because there's different resonances. So ours was a 500 megahertz. So that's what you need to include for that one. Same for both of these, okay? So you're gonna list out, you're gonna go back to your chart where you have things labeled and like this is a singlet, this is a doublet. So you're gonna go and you're just gonna list those right there, and she gives you an example of how to write it out. But as say for example, I'm gonna say 1.84 ppm and parentheses, it's a doublet, so that's a D, and then I need to put whatever else she has on there for it. So I'm gonna keep listing them out like that. Same for carbon NMR.